A model takes a cloud of points and, without any hand minus written rules, bends space until the colors separate cleanly. That bending is not a metaphor. It is literally what the math describes. Shapes moving, stretching, and rotating. This series is about learning to see that motion so the model stops being a black box and becomes a machine you can reason about. Most of us interact with models through code. You import a library, call fit, and get predictions. That's powerful, but it hides the mechanism. When something breaks, you can only guess. Maybe more data, maybe a different learning rate, maybe a bigger model. Without a mental model of what the math is doing, debugging becomes superstition. Here is the shift. Stop treating data as a spreadsheet of numbers. Treat it as a shape living in a space. A single data point is a location. A dataset is a cloud. A model is a machine that moves that cloud. And a prediction is often just a simple geometric test after the movement, like which side of a boundary you land on. To make that concrete, imagine a loan application described by a list of attributes: age, income, debt, and so on. That list is a vector, not an arrow you shoot through space, but a coordinate in a concept space. When you add more features, you are not adding mystery. You are adding dimensions, meaning more directions the model can use to separate patterns. Once you see vectors as locations, linear algebra becomes mechanics. A matrix is not a table. It is a function that moves every point in space in a consistent way. It can rotate, stretch, and shear. And a neural network layer is exactly that, a learned transformation. Training is the process of choosing the transformation that makes the classes geometrically easy to separate. Calculus is the same story, but for change. The loss is a landscape over the knobs of the model. A derivative is not just a slope on a graph. It is a sensitivity. If I turn this knob a little, how much does the loss change? The gradient collects all sensitivities into a single direction, the direction that increases loss the fastest. Probability enters when the world is messy and finite. Data is not a single point. It is a distribution, a shape of noise and signal. A model trained on one distribution can fail instantly on another. So we will learn to see uncertainty as geometry too: mass, concentration, and typical sets. That's how you understand generalization, robustness, and why normalization helps. So here is the promise of the series. We will build a visual mental model of three languages: linear algebra for transformations, calculus for learning dynamics, and probability for uncertainty. The goal is not to grind through algebra by hand. The goal is to see the mechanism clearly enough that when a model fails, you can predict why and design a fix.